In this video, we are going to discuss about the power requirements based on solar cell, vibration and thermal based wearable devices. Here, the energy harvesting can vary depending on several factors. So here are the general overview of their power requirements. First one is solar cell. Solar cell convert sunlight directly into electricity. The power output of a solar cell depends on various factors, including the surface area of the cell, the efficiency of the cell, and the intensity of sunlight falling on the cell. The power output of a solar cell is typically measured in watts or milliwatts. Common solar cells used in consumer applications can have power outputs ranging from a few milliwatts to several watts. To determine the power requirement of a solar cell systems, you need to consider the power consumption of the device you intend to power and the available sunlight in the location where the solar cell will be deployed. The power consumption should be equal to or less than the power output of the solar cell system to ensure proper operation. Small portable devices. Solar cells used in small portable devices like calculator or small electronics usually have power output in the range of milliwatts to a few watts. Next, it is used in residential solar panels, typically having the power rating which is ranging from 100 watts to 400 watts. Depending on their size and efficiency, these panels can produce kilowatts of power under favorable conditions. Next one, large scale solar farms. This is nothing but a utility scale solar farms. It can generate power of megawatts to gigawatts, supplying electricity to large areas or even entire cities. Next one is vibration based energy harvesters. This vibration based energy harvesters is also known as vibration energy harvesters or vibration powered generators, which convert mechanical vibrations or movements into electrical energy. These devices are often used to power low power electronics in application where there is continuous or intermittent vibration. The power output of vibration based energy harvesters depends on factors such as the amplitude and frequency of vibration. the design of the harvester and the efficiency of the conversion mechanism. The power output of a vibration based energy harvester is usually relatively low, ranging from microwatts to milliwatts. The power requirement of devices powered by vibration energy harvester should be designed to be within the power output range of the harvesters. Next one is thermal based energy harvesters. Thermal based energy harvesters are also known as thermoelectric generators (TEG), which converts temperature difference into electrical energy. These devices utilize the Seebeck effect, where a temperature gradient across a thermoelectric material generates a voltage. The power output of thermal based energy harvesters depend on factors such as the temperature difference across the generator, the size and the efficiency of the TEG module, and the heat transfer characteristics of the system. The power output of thermal based energy harvesters can ranges from microwatts to watts, depending on the temperature difference and other factors. The power requirements of the devices powered by thermal energy harvesters should be designed to match the power output capability of the harvesters. It is important to note that the power requirement and the power output mentioned above are general ranges and can vary significantly based on specific design, technologies and application. It is always recommended to consult the specification and data sheet provided by the manufacturers for detailed information on power requirements and capability of the specific solar cell, vibration based or thermal based energy harvesters. For low power application, this small scale thermal energy harvesters can generate a few microwatts to milliwatts of power, which is suitable for low power sensors, wireless devices, or low energy electronics. Next one is waste heat recovery. In industrial settings or power plants, thermal energy harvesting systems can potentially produce kilowatts to megawatts of power by recovering waste heat from various processes. Energy harvesting in wearable system. Personalized sensor network optionally should include wearable sensor or a BAN, that is body area network, wirelessly connected to a home computer or a remote computer through long distance devices such as a personal digital assistant or mobile phone. While long distance data transmission can typically be performed only by using the batteries as a power supply, the sensors with a short distance wireless link can be powered autonomously. The idea of a self-powered device is not new and is actually known for centuries. The earliest example of a self-powered wearable devices is the self-winding watch invented in about 1770s. However, typically not much energy is harvested in a small devices. So that use of a battery, primary or rechargeable is beneficial from practical point of view. There are worldwide effort going on for the development of micro generators that should eliminate the necessity of wiring and batteries in autonomous and standalone devices or in devices that are difficult to access. Energy harvesters are being developed for the same purpose. An energy harvester, it is also called as an energy scavengers, is a relatively small power generator that does not require fossil fuel. Instead, it uses energy available in the ambient, such as an electromagnetic energy, vibration, a wind, a water flow, and a thermal energy. These sources are the same as those used in power plants or power generators, such as the one for powering houses in remote locations, light towers, spacecraft, and on the transport. Except those based on the fossil fuels, right? An energy scavengers is typically several to 1 centimeter size power micro plant that converts into electricity any primary energy that is available in the ambient. The reason to call them harvesters or scavengers is the new application area they are used for powering small devices such as sensors or sensor nodes. This way of powering them eliminates the need for cost ineffective work such as wiring or either recharging or replacing batteries. An energy harvester could also be combined with the battery and serve a complementary source of power to improve energy autonomy of a devices at limited size of the battery. Three kind of energy source can be used for harvesting in wearable devices. These are the mechanical energy of people's own moving or acceleration on transport, and electromagnetic energy, that is mainly light energy, and the heat flow caused by the difference in the temperature between the human body and the ambient. There is a difference between truly unobtrusive energy harvesters such as photovoltaic cells, that is PV, and effort driven micro power generators. The typical example for the latter is a flashlight that is to be shaken or pre-powered by using the embedded dynamo. A power of the order of watts can be obtained in such efforts driven micro generator. However, this way of powering BAN, body area network, or wearable sensor should be rejected because of additional care required for the patient side. The worst case scenario for energy harvesting is a patient who stays in his or her bed. Then there is a practically no mechanical energy is to harvest, right? Since the person is always in bed and he is not able to move, how can we generate energy? The light intensity at home is low. The heat flow minimized because of a blanket and low metabolic rate, especially in elderly people. Therefore, only a part of the head and sometimes wrist of the person is the only relative small zone where energy harvesters of thermal or light energy can be located on such patients. The available power is low because the illumination level indoor is low and the heat transfer from the person is determined by natural connection around the head. Nevertheless, even in such case, powering of example health monitoring sensors by using energy harvester is feasible. Preventive healthcare is considered as a way to potentially decrease the cost of healthcare, which is steadily on an upward trend. One of the strategy is to shift the health monitoring and management outside the expensive medical center to family doctors and even to the home. For example, the monitoring of chronic diseases while providing real time data from and to the patient whenever he or she is and at any moment. Many of us significant potential for both cost reduction at the stage of monitoring and for making curative medicine cost effective. Wireless healthcare system, which could be an important component of so-called e-health or e-health grids, are expected to focus on preventive care and effective provision of continuous treatment to the patient, especially those living in remote location and to elderly people. Real-time monitoring of patients' vital sign and patient level health data requires the use of wearable sensors and mobile devices. It would be good if such devices are small, unobtrusive, and maintenance free for their entire service life. Some of my reference for making these videos I have given below. First one, Analysa Bonfiglo and Dilo D. Rossi. Wearable Monitoring Systems, Springer 2011. Second one book is Gong Zong Yang Body Sensor Network, Springer 2006. Third one is Fundamentals of Internet of Things, IoT and Wearable Technology Design, IEEE Plus Willy Higher Road. Fourth one, Wearable Sensor Fundamentals, Implementations and Applications, edited by Edward Sassunovo, second edition. So thank you for listening to this video.